This is Algebra 2 with trig, 7b.3. We're talking about infinite series. So what we're trying to do is add up a list of numbers that goes on forever. And a lot of times we think that that can't happen. But there is a situation where that can happen. Let's take this sheet of paper where we'll just pretend for easy numbers that this is 4 going across the top and 3 going down the side. So what is the area of this sheet of paper?
12.
So we have 3 times 4. We have an area of 12. So if I cut that in half, what is the area of that sheet of paper?
6.
So we now have an area of 6, right? So we're going to take this area. How much is this one?
3.
It's going to be 3. So we're going to put those two together. Now we're going to take half of what I have left. How much is this one going to be?
1.5. Look at us go.
Then I'm going to take what I have left and cut that in half.
0.7.
We got 0.75. Take what I have left. Cut that in half. We got 0.375. Cut that in half. 0.81875. Cut that in half. Cut that in half. Cut that in half. Okay, and mathematically, now I'm too far to go any further, but mathematically we can keep cutting them in half. So we keep cutting that in half, and this is the area of each little piece. What type of number are we looking at here? What does this -8 mean?
That many, or the decimal place moved that many times.
The decimal spot is moved -8, which means negative to the left, 8 spots, which would mean 7 zeros, 0.000000111175. So a very small number, but nonetheless, the number exists, and we can keep adding them all together. Now, what are all of these numbers going to add up to equal? They're only going to add up to the amount of the paper, where we could put that back together in some creative way, maybe. Like a puzzle. All right, and you can keep going. But we won't worry about putting all these other pieces together also. But no matter how many times we chop this in half, the sum is never going to be more than what it started to be. We kept cutting this down, and we knew that adding them all up was going to add up to 12. So that's what this infinite series means. So now you know that it's possible in some situations to add up a list of numbers that goes on forever. Tearing the paper was a good example of that. The sum S of n of the first n terms of an infinite series is called partial sums. So we can represent this in a graph. The partial sums of an infinite series may approach a limiting value. We've done where values approach, and we call that the asymptote. It's the same idea here. what we're going to do is take this series. We'll take 1/2, 1/4, 1/8, and so forth. We're taking half of it every time as we go. The same thing we did to this sheet of paper. The first total sum that we have is 1/2. So we're up at 0.5 for this first value. Partial sums, listen to the name of it. We're adding up the parts together. So then we're going to do 1/2 plus 1/4. To do that, we need common denominators. Our common denominators are going to be a 4. So it's going to be 2/4 plus 1/4 gives us 3/4. So that's 0.5, 0.6, 0.75. Then, just to make life easy, rather than doing 1/2 plus 1/4 plus 1/8 and getting all the common denominators and grouping them all together, we know that these two are actually 3/4 plus or 1/8. Now we can get common denominators. And if you multiply the 4 by 2, you got to multiply the 3 by 2. And this comes out to be 7/8. And with 7/8 in terms of a decimal, we have our 0.875. So our third time, we were up here at 0.5, 6, 7, 8. 8.5. 8.75. So we do our 1/2, our 1/4, our 1/8, and then the extra piece, the 1/16. We know that these three terms are all 7/8, and we're going to add the 1/16 to that. So we need common denominators, and that gives me 15/16. Well, 15/16 is even closer to 1. 0.9375. And we could even do it one more time where we have the 1/2 and the 4th and the 8th and the 16th and the 32nd. Well, we know all of these are adding up to 15/16 plus or 1 over 32 is going to give us 30 over 32, and 1 over 32 gives us 31 over 32. And you start to see a pattern. When we're adding these up in this situation, we're having 1 over 2, 3 over 4, 7 over 8, 15 over 16, 31 over 32, 31 over 32, 0.96. What's the next one going to be? What would S of 6 equal?
64.
We would double the denominator, just as they've shown, and the top is 1 less. So that's just looking at patterns at this point, and you see that we get closer to 1. And if we continue that pattern on and on, you could do the math to show that it's getting closer to 1. You're never going to reach 1. So what this is approaching is the total sum of this infinite series. So the sum in this case is 1. Let's take a look at this partial sum. Here we're taking the numbers 1 plus 2 plus 4 plus 8 plus 16 plus 32 and 64 and 128 and on and on. They've done the partial sums for us. We start out at 1. Then we're at 3. Then we're at 7. Then we're at 15. Then we're at 31. And it keeps growing. What is this approaching? It's going up forever. The 6 would have been the 6th term. Then we could have done the 7th term. We would have gotten the 6th term by putting 32 onto this. And then we would have gotten the 7th term by putting the 64 on top of that, and gotten the 8th term by putting a 128 on top of that. It would have kept going up forever. So infinitely. The partial sums approaches infinity. So it has no sum because it goes up forever. Here, the partial sums approaches the value 1. So that is your value that this infinite series is going to add up to equal. This one would add up to be infinity because it always gets bigger. Now, in this case, we don't actually connect the dots because there are not values in between the sum of 1 and the sum of 2. It's just the sum of the first number, the sum of the first 2 numbers, the sum of the first 3 numbers. There's no such thing as the sum of the first 3.5 numbers. So we don't connect the dots. We often kind of trace it out to see where it's going because we're so used to connecting them. But no, this is called a discrete graph, not a continuous graph.
Okay.
The values land exactly where the points are. So let's try this one, this partial sums. So we're taking the number 3 and 3.5 and 4 and 4.5 and 5, so it looks like we're going up by a half each time. So at the first term, we're up at 3. Second time, we're up at 6.5. For the second, adding all 3 terms together. The 3, that's 6. 4 is a total of 7, or 10, and the half would give us 10.5. Then we're going to add up all 4 terms. So we have the 10.5 plus 4 more, which gives us a total of 15. Then we're going to add the 5 onto that, or 5.5, I guess, and that would take us up even higher. So what are we seeing with the pattern here? Is that approaching anything? It's approaching infinity. The partial sums approaches infinity. Now, do you understand why this one is approaching the value of 1 and why this one is not approaching a specific number? It always keeps going up because we're going to be adding a much larger number every time. This one will be adding on another number, but the number is getting closer and closer to 0, so it's going up by less and less every amount. You could never reach the number 1, even when you keep adding on more. And I showed you the pattern with the calculator. So how does this work out for us to figure out the sum? Graphing is not a super productive way to do this. So we'll have a formula, the sum of the infinite series. the sum of an infinite geometric, it has to be geometric, with the first term of a of 1 and a common ratio of r, is going to have an infinite sum of a of 1 over 1 minus r. That is the total sum. So when we look at this pattern up here, we see that our first term is a half, and 1 minus, what are we multiplying by? What's a ratio? One over, what are we doing to each number down here? Times 2. So we're multiplying a half times 1/2 to get 1/4. And then 1/4 times a half to get 1/8. And 1/8 times a half to get 1/16. So this is 1 minus a half. So this is a half divided by a half, which is the value of 1. So you see how the formula creates that. Now, oddly enough, this has a, what's our R value here? Times 2, times 2, times 2. So the R value is 2. This is geometric. If we start with 1, and we say 1 minus 2, that's 1 over negative 1, which is a total sum of negative 1. That doesn't make a lot of sense. Right? So that's a good example of one that doesn't have a sum. But what I was trying to point out here is if you have a group of numbers, you might get a result, but you need to know that it's inappropriate to try to calculate out that sum because it doesn't exist because of the pattern of the numbers. You might get an answer and think that you're setting it up right, but you need to understand that if your R is too big, if it's greater than 1 or greater, it's not going to have a sum. So right here, we can use this geometric infinite formula when R is less than 1. Now, the absolute values, what does that imply? So when the R value, regardless of positive or negative, is less than 1. So the distance from 0 is less than 1. But down here, if the infinite series is geometric and the absolute value of R is greater than or equal to 1, the series has no sum. There will be no sum if the R value is too big. We kind of saw that example here. It's much more obvious that the graph is going up forever. If you have arithmetic, it doesn't matter anything about the numbers. The series has no sum. Arithmetic will not have a sum because it goes on forever. Only geometric will have a sum. So let's flip it over. Let's practice a couple of these. So we look at our first example. What do we see? We see that the format here, the A of 1 would be a 1. We have a common ratio raised to a power. So I know this is geometric. The A of 1 value is 1, and the R value is 0.8. So the R value is less than 1. So we can find a sum. So the infinite sum formula is A of 1 over 1 minus R. So that's 1 over 1 minus 0.8. So 1 over 0.2. So if you take the 1 divided by 0.2, we'll get the value of 5. So our sum of this series, this is sigma notation, has a total sum of 5. If you found what the first term was, the second term was, and so forth, and put them all together, you would add up to a maximum of 5. Our next one. What do we see looking at this series?
It's squared.
Okay, dot, dot, dot tells us that this is infinite or infinity. It goes on forever.
Because 2 squared is 4.
So one way that we can test for geometric is to take the term divided by the one before it. And that's clearly negative 3/4. We can take 9/16 and divide it by the term before it. And that's going to be 9/16 times the reciprocal. When you're dividing by a fraction, you divide by, or you actually multiply by the reciprocal. And here we can reduce. 4 goes into 4 once, 4 goes into 16 4 times, once, and 3 times. So we're getting 3/4 with our negative. So negative 3/4. So we're getting a common ratio. That proves, or that supports, that this is geometric. So where the R value is negative 3/4 and the first term is clearly 1. So our total sum is going to be A of 1 over 1 minus R, which is 1 over 1 minus negative 3/4. If we use our calculator, we get a crazy decimal. I'll show you it both ways. We could do this by hand and say 1 plus 3/4. To do that, we need to have common denominators of 4 over 4 plus 3/4. So that gives us 1 over 7/4. And we just talked about if you're dividing by a fraction, you have to multiply by the reciprocal. So there's our total sum. If we were to use a calculator, you could say our A of 1 is 1, divided by, use your parentheses, 1 minus negative 3/4, just to make life easy, we'll say 0.75, and we get this crazy looking decimal. If you hit the math button, you can look at fraction, and it'll turn your previous answer into a fraction, and that's going to be 4/7.
You know, if we learned about this yesterday,
Okay, what about the next one?
isn't it not a sum?
What do we know? We see that this is geometric, but the R value is greater than 1. So there is no sum. No sum for that one. Now, a lot of people look at this and they see the fraction and they just automatically think, okay, it's a fraction, it's less than 1. But that's not true. This is 1.25. The numerator is larger than the denominator. It's a value that's greater than 1. Let's look at this last one. What do we see? What type of series is this? It is infinite because it's ending with the ... So it's infinite. Notice that 1 divided by 5 is different than negative 3 divided by 1, which is different than negative 7 divided by negative 3. It's not geometric. So we could stop right there. It's not geometric. But if we do notice, this is down by 4, down by 4, down by 4. This is arithmetic. So it has no sum. When you keep adding those numbers together, these numbers are going to get to be very negative, and it's going to add up to be a negative answer, but it just keeps getting further and further negative every time you add the next value. So because it's arithmetic, there is no sum. Because the R value is greater than 1, there is no sum. It would really be greater than or equal to 1, but nonetheless, it's greater than that. All right, last one. We're swinging a pendulum, and the first swing is going to be 18 inches. And the next swing is going to be 80% of that. It doesn't continue at the same momentum forever. We're dropping 80% every time. So the first swing is 18. The second swing is 18 times 0.8. We get 1440. The third one's going to be 1152. The next one's going to be 921, some change. And so forth as we're going. We're taking 80% of the previous number every time. On 5 swings, we have even more. So this does continue. And we keep swinging. And the pendulum keeps going back and forth. And we finally see that we're not adding very much. But it is always something. What is the total distance that this has swung by? This is geometric with an A value of 18 and an R value of 0.8. So our infinite formula is A of 1 over 1 minus R, so that's 18 over 1 minus 0.8, 18 over 0.2, which comes out to be 90. So all of those numbers added together is going to add up to be 90. Mathematically, you'd never reach 90. You would have to keep adding on the next one and the next one to get yourself closer and get yourself closer and get yourself closer to the value of 90.